This is section 9.6b, permutations and combinations. Today we're going to talk about combinations. In the last lesson we saw permutations. Today we'll talk about combinations, and for combinations order does not matter. So a good way to remember that is with permutations order matters. With combinations order doesn't matter. That's the main difference. And we'll see specific examples to illustrate that. But that is the best way to remember the difference. So different combinations are possible only when a subset of total elements is taken. For example, in this class of n students, there are n factorial permutations, but only one combination. All right, and that makes sense because if in a combination order doesn't matter, well then, a group of James, Mike, Bobby, Susie, and Alan, it doesn't matter what order you put them in, it's still the same group. Okay, now for that same group of 5 students, James, Mike, Bobby, Susie, and Alan, there could be different permutations, different ways of ordering those 5. But if we're looking at a combination, well, there's only one combination for that group of 5 students because order doesn't matter with a combination. Okay, so all of that just to illustrate that for combinations, they really only make sense when you're taking a subset of a larger group. Now, you don't need to remember that for the test, but it's just to help you understand what combinations are. And the remaining things that I'll do on this screen are really just to understand what combinations are. You don't really need to worry about the math techniques yet. So here's a specific example of a permutation. And this is just to kind of review what we already learned, because now we're going to compare permutations to combinations. The number of possible first, second, and third place winners in a class of 15 is 15p3, and that's 2,730. Again, don't worry about calculating the 2730 yourself. We're going to get to that later, and you did some of that in the last section anyway. What I want to do is just kind of show you the difference between permutations and combinations. And so let's look at the next example. The number of possible 3-player volleyball teams in a class of 15 is 15C3. And that turns out to be 455 with techniques that we're going to learn. All right, so why did I put these two examples one after another? Because one is a classic permutation and the other one's a classic combination. And this just helps to illustrate why order matters. You see, first, second, and third place winners. If James is first place and Christine is second place and Bobby is third place, that's not the same as Christine being first place, Bobby second, and James third. All right, order matters. Order matters, and that's why that's a permutation problem. But notice that for the 3-player volleyball team, order doesn't matter because the 3 players, they rotate, and they all are helping each other out. We're not saying that there is a player 1, a player 2, and a player 3. It's just that there are 3 players who form a team. So order doesn't matter. Order doesn't matter. Now you might ask yourself, well, when can I tell that order matters, and when can I tell that order doesn't matter? And really the only answer to that is you have to get it from the wording of the problem. And with practice, you recognize when order matters and when order doesn't. Usually, if you think about the problem and ask yourself that question, you'll be able to answer it. Does order matter, or does order not matter? Okay, so again, this screen is really just qualitative. What I'm saying is I want you to understand the concept. We're going to get to the quantitative techniques later. But let's see if you can observe or notice something. How does the size of P compare to the size of C? All right, well, obviously, P is a lot bigger. Okay, so we can see that the permutations, or 15P3, is a lot bigger than the combinations 15C3. All right, and the reason that's true, you probably already figured it out, is that there are a lot of ways to, to order 3 different people. You can have James, Bobby, Sally, Sally, Bobby, James, etc., etc. You know, there are 6 different ways to order 3 people. But for a 3-player volleyball team, there's just one way of having the 3 people because it's a combination and order doesn't matter. All right, so that qualitatively helps us to understand why there are always more permutations than combinations. But what I'd like you to do now is see if you can figure out how much bigger P is than C. So I don't want you to spend a lot of time on this, but pause the video, try to figure that out, and then resume after, if you get stuck or when you have an answer. All right, hopefully what you discovered is this, and if you didn't discover it, that's okay, because we're going to talk about it more later, but C equals the number of permutations, or P, divided by 3 factorial. Why 3 factorial? Because 3 factorial describes all the different ways that you can order 3 members. That's when order matters. Now, this is a combination problem, and since order doesn't matter, we have to divide the number of permutations by the different ways of ordering each subset, and that will give us our final answer. Okay, so since 3 factorial is 6, then for this specific problem, C equals 2,730 divided by 3 factorial, which equals 2,730 divided by 6, and that equals 455. Okay, so this shows us not only that combinations are, of course, always fewer than permutations, since order doesn't matter, but it also shows you by how much fewer they are. You need to divide the number of permutations by all the different ways you can order the subset. And again, if you don't really like derivations so much and it doesn't interest you, that's okay. We're going to learn the formulas for these. But I think it's important to at least have some idea of where the formula comes from, because otherwise you're really just, memorizing and not understanding the math. A combination of n elements taken r at a time is a subset of the collection of elements where order is not important. Again, sounds complicated, but as we saw in the last section with permutations, it's really not that complicated. The formula for the number of combinations of n elements taken r at a time is NCR. All right, so n represents the number in the collection, the total number. R represents the number taken from the collection, or the subset. And that's given by n factorial divided by n minus r factorial times r factorial. Now, look at the arrow that I'm using here to highlight a certain part of the combination formula. Notice that I'm circling n factorial divided by n minus r factorial. Okay, you'll probably recognize from the last section that that's equivalent to the permutation formula, because really when you're looking for combinations, it's the permutation formula but divided further by the number of ways you can order the subset. Okay, so that's where this formula comes from. Now, in the last section, we derived this formula, n factorial over n minus r factorial, for NPR. And the only difference between NPR and NCR is that you also have an r factorial in the numerator. And this, we can visually here remember, we can recognize that NCR is always going to be smaller than NPR because you're dividing further by r factorial. So going back to the example on the last screen, which was 15C3, that would equal 15 factorial because 15s are n, 12 factorial because 15 minus 3, or n minus r, is 12, and 3 factorial because my r is 3. 15 factorial divided by 12 factorial times 3 factorial, and that equals 455. Also, as we saw on the last screen, and I'm going to use the mouse arrow again to highlight a certain portion of this formula, notice that the 15 factorial divided by 12 factorial, 15 factorial divided by 12 factorial, is equivalent to NPR. And so all NCR is just this NPR number divided further by R factorial. And that's why 455 is so much smaller than 2730. So putting this in words then is that if I have a class of 15 people, or if you like, you could say a group of 15 athletes, and I want to form many different 3-player volleyball teams from that pool of 15. Well, then there are 455 different volleyball teams that I can make. 3-person volleyball teams that I can make from a group of 15 athletes. Another example, how many different ways are there to choose 6 books from a set of 10 books if the order does not matter? Alright, now normally problems aren't going to just give you such an obvious hint, but since it explicitly tells us order does not matter, then you should be able to tell whether we're talking about permutations or combinations here. Anyway, pause the video, do this on your own, and then resume when you have an answer. Alright, so order doesn't matter, and therefore we're going to use NCR. My N is 10, my R is 6, and 10C6 equals 10 factorial over 4 factorial times 6 factorial, and that equals 210. Now there's another way to do this on your calculator if you don't want to enter the factorials in. And you have to actually go to the catalog, go to the catalog button and choose the function which is NCR. There's an NCR function there. And you just enter the number n, then the NCR function, and then the number r, and it'll calculate it for you. You don't need to waste time trying to figure that out on your own. If some of you would prefer to do it that way and can't figure it out, then just wait till you get to class, and I can show you how to do that, or you can get it from another student. In any case, you can easily evaluate this on your calculator. 10 factorial over 4 factorial times 6 factorial, and that equals 210. So that means for these 10 books, if I want to take six books out of that set of 10, and it doesn't matter what order I put those 6 books in, there are 210 different ways to have a subset of 6 books from the total set of 10. All right, let's look at a poker hand. You know that a standard deck of cards has 52 cards in it. There are 13 different cards of each suit. So there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And the question is, how many 5-card poker hands are possible in a standard deck of cards? Alright, so you should pause the video, do this on your own, and then resume when you have an answer. Alright, you should have recognized that this was a combination problem. Why? Because the order of your hand doesn't matter. If you have an ace of hearts, a 2 of diamonds, a 3 of hearts, a 4 of diamonds, and a 5 of clubs, that's the same as having a 5 of clubs, a 3 of hearts, a 4 of diamonds, a 2 of diamonds, and an ace of hearts. It doesn't matter. What matters in poker is just the 5 cards that you have. You can arrange them in any order you want in your hand, and that doesn't matter. The value of the hand remains the same. Alright, so this is a combination problem, and my N is 52, that's why I have 52 here. My R is 5, my subset, because it's a 5-card hand. And this number, 2,598,960, this is the number of all the different possible 5-card poker hands that you can get in the standard deck. Another example, and this is a little bit harder. You're going to need to think about this one. You're making a 10-member basketball team from 9 girls and 12 boys. The team must consist of 4 girls and 6 boys. How many possible teams are there? All right, well, you probably have figured out already that this is a combination problem. Because, when you're dealing with teams, order doesn't matter. But what you need to figure out now is how to put this together. Okay, we're actually talking about 2 combinations that we're putting together. So that's your hint. Pause the video, try to do this on your own, and then resume. So this is what you should have come up with. 9C4 times 12C6 equals 116,424. All right, where did we get this from? Okay, so the 9C4 accounts for the 4 girls who will be on the team. Okay, so there's a total pool of 9 girls, from which 4 are chosen. And then the 12C6 accounts for the 6 boys who will be on the team. There's a total pool of 12 boys, and that would be our N in this case, 12, from which 6 boys are chosen. And 4 girls and 6 boys will give us a 10-member basketball team. Now, why do we multiply them? You might have figured this out on your own already, but what this means is that for any group of 4 girls, and remember that there are a lot of different possible groups of 4 girls from the pool of 9. For any one of those groups of 4 girls, there are many different groups of 6 boys that can go with that group of 4 girls, and that's why we have to multiply. That's why we have to multiply, because these are like independent events. You could call this your girl event and this your boy event, and with independent events, as we learned before, you need to multiply them to get the total number. So 9C4 times 12C6 equals 116,424. Classwork, page 699. Please write these numbers down, and we'll see you in class.